So, welcome back to lectures on engineering mathematics 2, and today we will talk about the line integrals. So, here what are the complex line integrals and what are the properties of complex line integrals, and then how to evaluate such line integrals. This we will cover today in this lecture. So, we have already discussed this line integral in the context of vectors, and very extensively we have derived results and discussed all terminologies coming for the line integrals. So, here since there is no new idea which is coming up for the line integrals in this context of the complex, we will go through some of the concepts quickly and come to the evaluation part, where we will observe again how to evaluate such a complex line integrals. So, here just to go quickly, that let fz be a continuous function of a complex variable z in some domain D, then the integral of fz along a path C. So, we have a path C in some domain here D is denoted by this notation. So, integral over C of fz dz, a similar notation we had earlier in the context of vector. So, the C is called the path of integration, and it may be represented parametrically similar to again for the vector context as zt, where xt plus iyt. Remember, there we used to have this like zt is equal to xt, the unit vector in the direction of x axis, and then yt in the z in the direction of y. So, we were defining the vector quantity by this xt yt, the two components. In this context, we have this in terms of the imaginary or the real part. So, we denote similar to the earlier one, but the notation we will follow from the complex context. So, zt is equal to xt plus iyt, and t varies from a to b, and again a similar sense of increasing t is called the positive sense of c. So, as we move along this t here, so we must be moving on this curve, and this increasing values of t, the direction we are moving on this curve is called the positive sense, positive direction of C. Well, so coming to the line integrals. So, the idea is same for all integrals, whether it is a real or complex. So, for instance, from z0 to zn we want to integrate along this given curve C, and our function is, let us say, fz, which we are integrating. So, we will break this curve into small curves or small sectors, and suppose in this sector here from zm minus 1 to zm, we have a point here which is denoted by xi m. So, how this integral, what is the physical meaning and how do we define it will be clear now. So, this is a summation here over all these small sectors. M goes from 1 to n, let us say these are the n sectors, and f, the value of the function evaluated at this xi m, and this difference here zm and zm minus 1. And if we sum this and take the limit n approaches to infinity, that means this number of sectors which we have divided, that is approaching to infinity now. So, as we approaches to infinity, this width will go to 0, and eventually the error which we were introducing, but just by subtracting zm to this zm minus 1 will go to 0, and we are eventually integrating over this given curve. So, when we take the limit of this summation, this is what we call the integral of this f over this c with respect to z. So, this is the physical interpretation. And if C is a closed path, then this line integral is will be denoted by this symbol here, the line integral over this closed path C f z dz, And coming to the basic properties, they are very much similar to the real integrals. So, what we have, the first property is the so called linearity. So, the linearity means that if we have this integrand here k1 f1 z and this k2 f2 z, we are integrating over z. So, the linearity says that we can have sum of the two integrals. So, the k1, because it was a constant, f1 integrated over dz, k2 as another constant there, and this integral over f2. So, this is the linearity property common for all integrals. So, here also for line integrals this is valid. Another property is for instance here the direction change. So, if we are going here from z0 to z f z dz, and now in the right hand side we are moving from z to z0. So, we have changed the direction, the orientation. So, the minus sign will just appear in front of the integral. Another property that we have a curve C here, which we can think of as sum of two curves C1 and C2. So, we have two curves, for instance this is C1 and then we have here C2 curve. So, we can break this whole curve into two parts. So, the first integral over C1 and then integral over C2. Another interesting inequality, so called this also ML inequality is well known. So, this fz is integrable along a curve C whose length is L. So, we have a curve here whose length is L, and suppose that there is a positive number m. So, such that this value of this, the absolute value of this fz is always less than equal to m on this curve, on the given curve. Then what we have, this inequality here, the absolute value of this curve integral fz dz over this C, we can bound by m into L. So, this integral is nothing but we can also write like fz and dz, and this fz absolute value of fz. So, this will be less than equal to, this integral will be bounded by this integral, and this fz is bounded by this m. So, we have this bounded by m and this curve integral this dz, and this is nothing but the length of the curve. So, if we just integrate over the curve C, we will get the length. So, that is ml. So, this is what we have here, that this integral is bounded by the ml. M is the upper bound for the function, the absolute value of the function, and then L is the length of the curve. So, this is also valid here for the curve integral. A similar inequality we do have for real integrals as well. Okay. So, there are various other properties of the integral, we are not going through all of them. Now, we are coming to these some terminology, the simple closed curve. So, all these terminologies we have discussed already in the vector calculus. So, there also we have talked about the line integrals. So, all these terms which I am just revising again, we have already discussed in previous lectures. So, a closed curve that does not intersect or not touch itself anywhere is called the simple closed curve. And for instance, this curve is not touching itself or crossing itself. So, this is a simple closed curve. Closed means the starting and the last point are the same. So, it is closed, and for instance this one is intersecting at this point here. So, this is not a closed curve. So, sorry, it's a closed curve, but it is not a simple closed curve. So, it is not simple though it is a closed curve. Okay. So, here we will be talking about the simply and multiply connected domain, which was already discussed in detail. So, domain D is called simply connected if any simple closed curve which lies in D can be shrunk to a point without leaving the domain D. That means, if we talk about this one, this is the domain D, we can take any simple closed curve here and we can shrunk this or this curve can be shrunk to a point here without leaving, I mean continuously shrunk here to this point without leaving the domain. So, this is what we call the simply connected domain, and for instance here all curves cannot have this property. If you take this one, okay, this can be shrunk to a point without leaving the domain, but if I take for instance this curve here and if I try to shrink it to one point, this is not possible because this is not a part of this, or this is not a part of domain. So, this here and these holes are not part of the domain. So, we cannot shrink such a curve to a point continuously without leaving the domain. So, this is not a simply connected domain, or this such domains we call multiply connected domain. So, these are the two types of regions domains we will be considering now. Smooth and piecewise smooth curves, we had enough discussion there. Just to remind you, so if we have a parameterized curve z is equal to zt is smooth when this z prime t exists and it is continuous, and there was one more condition which we have elaborated there, that this derivative should not be equal to 0 for any t. So, we call such a curve is a smooth curve, and there was a term piecewise smooth. So, piecewise smooth means the curve is smooth in pieces. So, if we have several pieces, let us say, of this continuous curve, then each piece has this property of smoothness, and as a whole we call this piecewise smooth curve. Okay, now coming to the evaluation of the line integrals. So, there are basically at least two ways we can evaluate these integrals, or we will discuss two ways to evaluate the line integrals. The first one, let us see piecewise smooth path, smooth curve, which is represented by this z equal to zt, where t lies between a and b. So, if this fz is continuous function on C, then we have this line integral C fz dz can be evaluated just by this integral here. The f, we substitute this parameterized function here zt for z, and then its derivative here z dot. So, this is the derivative. So, then we can evaluate this line integral. So, I am not discussing much into the details of this because we have already discussed such curve integrals or line integrals in vector calculus. There also we had the same formula for the evaluation, and which was also look into that how do we get such a formula and so on. All other details one can find in the lectures on which we have discussed on vector calculus, and there was a section where line integrals were discussed. So, here coming to this one, so this is the one approach which we can obviously use for evaluating these line integrals. The another would be that if a continuous function f has a primitive, so primitive means the antiderivative. So, if it has a primitive f in D, that means if there is a function whose derivative is exactly this given function f z for all z in D. So, this is also important, that in the domain, in the whole domain we have this primitive, and then for all paths. So, any path we can take C, any path C in this domain D, which joins for example these 2 points. So, we have a domain D where the function f has primitive, then between these z0 and z1 point, these are the part of these points belongs to this D. We can take any path here, any path we can take. So, this is like C1 path, C2 path, or any other path, C3 path. So, we can take any path, and then we have this value of this line integral just f z1 minus f z0. So, this is path independence which we have discussed there. So, here this value does not depend on the path, which path you follow from to go from z0 to z1, because your function was having this primitive there f big F here. So, whose derivative is the given integrand here f. So, this value of this integral is just f z1 minus f z0. So, we can take a look how to get this formula, this value, using the above definition of the integral. So, how to get this one? This is what we can just closely, very briefly look into it. So, if z, let us say this zt is the parameterization of this smooth curve. So, we are talking restricting to our smooth curves, but this can be done for piecewise smooth curves, for instance. So, this z at A is the initial point z0, and z evaluated at B is the z1 point. So, we have the 2 points there in the domain z0 and then z1. We have a parameterized equations for the curve, any curve you can take here. So, the parameterized equation for some curve is given by this zt. So, this integral, line integral fz dz, we can write down f, and then we substitute this zt, that is the formula we have discussed first, and its derivative. So, f is given as f prime. So, here because it has a primitive, so f prime zt and then the derivative of this zt dt. So, this we can write the chain rule. So, this is coming exactly from the chain rule. So, the derivative of this f z t with respect to t is the derivative of this f with respect to z and the derivative of z with respect to t. So, this we can write down here, and then so this is the derivative, and then we are talking about the integral. So, this is just f z evaluated at b minus f z evaluated at a, and this z b and z a were exactly z 1 and z 0. So, this integral or this curve integral, when there is a primitive existence of the primitive in the whole domain D, then any curve we can take, the value will depend on the initial and the final point, not on the curve itself. As a consequence of this, if we have the closed curve, for instance, so if we are talking about the closed curve there, if our integral is over the closed curve, and all these conditions are fulfilled, that this f has a primitive. So, in the whole domain, which included by this, enclosed by this curve C, then this is going to be 0, because initial and the final points are the same there. So, f z1 minus f z0, this will become 0. So, that is a consequence of this result. There is another important result which naturally we will not prove, because that is a bit involved. So, let this f z be analytic in a simply connected domain. So, if we have a function f z which is analytic in a simply connected domain D, then f has a primitive in D. That means there exists this f z such that f prime z is equal to f z. So, that is also a very important result, which this above result can be used now for analytic functions. So, if we have f z analytic function, instead of saying this if f is a continuous and which has primitive, so we can say that if f z is analytic in a simply connected domain D, then this formula which we have discussed above, that the value depends only on the initial and the final point, is also valid. So, not only that the function has to be continuous and it has the primitive, those conditions are not explicitly required. So, analyticity of f z in a domain D is also enough to use this above formula, that because this says that if f z is analytic, it has a primitive, and if it has a primitive, we can use this direct formula for the integration. So, we will also utilize this now in our evaluation of line integrals. Well, so this is one example which we will discuss here for the evaluation. So, we want, because this is also important example which we will use its value later on, we will not every time evaluate this. This is a standard example. So, we want to evaluate this closed over the closed curve C. This the integrand is z minus z0 power m dz, and m is an integer and C is the circle of radius rho and center at z0. So, we have the center z0 and the radius is rho for the circle where we are integrating this function. So, the case 1 we will consider that m is greater than 0, because it depends on the different values of m what will be the value of this integral. So, if m is 0, that means the integrand is 1. So, naturally it is a simple case, and m is positive also. So, what is interesting here, that z minus z0 power m, when m is non-negative number, so m is greater than equal to 0, this is analytic, because there is no point where the function has any problem for getting its derivative. So, this function is analytic in on the C and the domain contained in enclosed by C. So, this function is analytic, and we have just learned before that once the function is analytic, and we can easily use the formula there, this in terms of the primitive f z1 minus f z naught, the initial and the final point. But here we are talking about C, which is a circle, so it is a closed curve. So, hence on this z minus z0 power m, this value will become 0. So, z minus z0 power n dz, this is analytic here on this closed curve. So, the value is 0. So, without any, we can use obviously the first formula for we can parameterize it, and then we can use this formula, naturally we will get 0, but we know this is analytic. So, we do not have to go through all these parameterization and using that formula here. So, this value is 0 in this case when m is greater than or equal to 0. This is the one result we have. The second case we will consider when m is equal to minus 1. So, if m is equal to minus 1, our function is 1 over z minus z0. So, in this case this is not analytic in this domain here, which contains this z0 point and this curve C. So, this function is not analytic, because at z equal to z0 there is a problem, the function is not defined indeed here. So, we cannot say that the function is analytic in this whole region enclosed by this curve C. So, in this case, since it is not analytic, we cannot use the above result which says that over the closed curve the value will be 0. So, we have to evaluate this, it may be 0, may not be 0. So, we need to evaluate using the definition, using the formula for integral. So, if C is a circle of radius rho and center z0, we have to parameterize this. So, we have the center z0 and the radius rho, we can parameterize this easily. So, z is equal to z naught and plus this rho times rho is the radius here, cos t plus I sin t. So, as we move along this t from 0 to 2 pi, we will be moving here in this direction on this curve. So, we need to parameterize this. So, this is the parametric equation of this curve, z is equal to z naught plus rho e power I t, and t varies here from 0 to 2 pi, and in the anti-clock direction we have the positive direction of this movement on the circle. So, having the parametric equation, it is easy now to evaluate the integral, this 1 over z minus z0. We have to substitute this z there in terms of the parameter t. So, that means the t is 0 to 2 pi, and then we have rho e power I t, that is this z minus z0. So, from this equation, from this parametric equation, we have basically z minus z0 is equal to rho e I t. So, we can just substitute for z minus z0 rho e I t, this power minus 1, and then we need for this the derivative of this, the derivative of this z. So, that means this dz over dt we can get. So, this is z naught, the constant. So, rho e power I t, and then 1 I will also come. So, rho into I and e power I t, and then we have dt. So, this is the formula for the integration which we have used here, and just to note that this rho with minus 1, this will get cancelled, e power I t will also get cancelled. So, over this dt, and we have just the 2 pi and I, because this I will remain in the integrand, and then we have the integral, so I and then 0 to 2 pi and dt. So, this is 2 pi I. So, the value of this integral over this given curve is 2 pi I, it is not 0. So, we have seen, because the function this was not analytic. So, over this closed curve also we have the value 2 pi. So, this case we have covered when this m was equal to minus 1, and when m is less than or equal to minus 2, we will also see that what value it will take. So, we consider this integral. Again we will substitute this parametric equation, so similar to the previous one. Then we have here e power I t and m plus 1 dt, and then we can integrate this. So, naturally m not equal to minus 1, that case we have already discussed before. So, we have this integral here, and then we can substitute the 2 pi for t and then 0 with the minus there. So, we have this integral. So, note this is here we have I and 2 m plus 1 pi, that means the cos 2 pi with this m plus 1 and plus this I sin 2 pi, the product with m plus 1. So, this sin 2 pi is going to be 0, the cos also 2 pi with number here, the integer, this is going to be 1. So, this value of this is going to be 1 and then minus 1. So, we will get 1 minus 1, which is 0 there. So, the value of this integral when m is less than equal to minus 2 is coming to be 0. So, what do we get? This line integral for all values of m, if we write down here. So, m is equal to minus 1, the value was 2 pi I, and m is not equal to 0, the value is 0. So, we have 0 and 2 pi. This is a very standard integral, which this value we are going to use again. Only when m is not equal to minus 1, the value is 2 pi. Other than this, for any value of m, the value is 0. So, a complex integral depends not only on the end points of the path, but in general also on the path itself. So, as we have seen here, it was a closed curve, but we have still the value there. So, it does not just depend on the end points, but it also depends on the path as well, which we will observe again in the next example, that this evaluation of this z conjugate is done from z is equal to 0 to 4 plus 2 I along the curve C, which is given by this parabolic curve z is equal to t square plus I t, and in the second case we will take z equal to 0 to z is equal to 2 I, and then from 2 I to 4 plus 2 I. So, let us take in the picture, we have the two paths here, the one is here. So, along this path t square plus this I t, the second path we are first moving from 0 to this point 2 I, and then from 2 I to we are going from 4 plus 2 I. So, variation in x along this and a variation in y along this one. Okay, so, this z bar we have already observed, it is not analytic. So, we have to therefore, we expect different values along the different path. It may not depend only at the beginning and the end point of the interval. So, let us just compute this. So, first z equal to 0 to this corresponding to these 2 points. If we look at the parametric equation, this z is equal to t square and plus this I t. So, the t equal to 0 we are at 0 and t equal to 2 we have 4 plus 2 I. So, the end point. So, that in terms of t we are varying from 0 to 2. So, that means this line integral 0 to 2 t, then we have substituted here the parameterized form, that means t square plus I t and its derivative. So, the dz over dt, given that z we have 2 t and plus I. So, this is here and then integral over dt. So, this simple integral we have to evaluate now. So, this product we can make and then over t we can integrate. So, after this integration we observe that the value is coming this complex number 10 minus 8 by 3 I. Now, the second part we will choose the other path here. So, first we will go from 0 to this 2I, and then again we will vary in the direction of x. So, we have two curves basically, the C1 and then we have the C2 curve there. So, the C1 is x equal to 0 and y is varying from 0 to 2. If we take this z is equal to x plus iy, along this C2 the y is constant, the y is kept constant, x is varying from 0 to 4. So, in the first one we will, for z we will put, because x is 0, so we have iy, so iy and the absolute the conjugate, and then the dz will be just I. So, dz in this case will be I dy. In the second case this will be just dx, and we have substituted for this z because y was 2 there. So, y is fixed here, x plus 2I, and along this dx we can vary. So, here we have y dy, because this I with I will be minus I there and I, so this will become 1, and you have this x minus 2I, so over this dx. So, just to get this integration can easily be performed. So, we are getting 10 minus 8 I as the value of this integral along this path p. So, what we have observed that along these two paths we have two different values, which is because of this z bar was not analytic. If the function is analytic, then it will not depend on the path, it will depend only on the beginning and the final point, the end point. So, these are the references used for preparing this lecture. And just to conclude, so what we have learned, we have learned this line integral. So, the basic definition for the line integral, or how to evaluate this. So, we need to parameterize z equal to zt, and then this curve integral can easily be evaluated by substituting this parameterized form in this f, and then its derivative and integral over dt. The second case, we have seen that if function is continuous and has a primitive, or we can replace this, we say that f is analytic in a domain D, and then we can take actually any path, because the integral value will not depend on the path, it will depend only on the final point and the beginning point. So, here this is also very useful in many cases once we know that the function has primitive, or in other words the function is analytic in a given domain. We can also use this second part, very useful, but this can be used for any cases, whether function is analytic or it is not analytic. We can use this evaluation here based on this parameterized form of the curve. So, that is all for this lecture, and I thank you for your attention.